Welcome back, students. In this video, we're going to look at the ozonolysis reaction of alkynes, which is sometimes also called oxidative cleavage. First, let's start by reminding ourselves what happened when we used alkenes for this reaction. When we had alkenes for this reaction, we saw a chopping of the pi bond this direction, and where we chopped, we added oxygen. When we cleave an alkyne, the difference is instead of a singular pi bond, we have two pi bonds now. And we can't make triple bonds to oxygen. So what is that going to look like? Well, we're still going to get cleavage here. The difference is now we're going to have three bonds to oxygen. One of them is going to be a double bond, and one of them is going to be a single bond. And that's starting to look a heck of a lot like a carboxylic acid. But you know what? That oxygen needs a proton. Oh, I wonder if that's what the water does. And we end up having a carboxylic acid at the end. Because the left-hand side of this is the same as the right-hand side, we get two of the same molecule at the end. So you can balance this equation if you wanted to, or you could draw both products. It depends upon what your teacher wants. If you're in my class and you forget to balance it on a test, I forgive you. Now, what if your alkyne was asymmetrical? In that case, you would get a mixture of products. So we would still see cleavage here, but the left-hand side is no longer the same as the right-hand side. So you're going to get two different products, and in this case, you have to draw both. Now let's make sure we don't miss any carbons. Right here, we're going to start with 1, 2, 3 carbons in our first structure. So 1, 2, 3. At that first carbon, you're going to have a double bond to oxygen and then an OH. At that second position, remember you had a methyl, so we have to draw that in. For your other compound, you had 1 and 2. So you have just 2 carbons in here. And at the first carbon, you have a double bond to oxygen and an OH. Now, what if we had a terminal alkyne? So an alkyne that had a hydrogen on one end. Remember, those internal alkynes are the ones that are in the middle. They have carbon on either side. But a terminal alkyne has hydrogen at least on one side. In this case, something really interesting happens. We're still getting cleavage here, and all the normal stuff happens to this side. So the side I highlighted in yellow follows the same pattern that we've been looking at. You have 1, 2, 3 carbons. So here are my 3 carbons. At that first position, you have a double bond to oxygen and an OH. The weird part is what happens to the other side. You only have 1 carbon. Have you ever heard of a 1-carbon carboxylic acid? Oh, you haven't? Okay, because it's not a thing. So you know what's the closest, though, is carbon dioxide. So you end up getting carbon dioxide from cleavage of the terminal alkyne. So that's where this one comes from. If you want to look at the mechanism, you'll probably have to Google it because I don't think it's in very many textbooks. Let's wrap up. In this video, we looked at oxidative cleavage, where we go through an ozonolysis reaction and ozone cleaves the pi bonds, well, and the sigma bond. When you utilize an alkyne, you end up getting a carboxylic acid most of the time, unless you have a terminal alkyne, and then you're going to get CO2 as one of your products. Be sure that you're watching out for writing multiple different products if your alkyne is asymmetrical. Thanks so much for your attention. This is Katoni signing out.